Welcome back. Now we will talk about the case where the channel is known as the transmitter. So this would be this case where you have transmitter with multiple antennas. You have a receiver with multiple antennas. There's a channel in between. Transmission is in this direction, but we assume that we have maybe some feedback channel which provides knowledge of the channel in some estimated form to the transmitter. So transmitter on the left, receiver on the right. And now the question is, how can the transmitter exploit knowledge of this channel to improve the transmission? To do this, we rely on a tool from matrix decomposition, and this is taken from this Wikipedia page. I highlighted some of the compositions that I think are important, but in particular today we will use something called singular value decomposition, or SVD. But I would say in general, as a communication engineer, or even as an electrical engineer, knowing your matrix decompositions can be very helpful. So our case now is when we have channel state information at the transmitter. We will use the tool of singular value decomposition, and this works as follows. Suppose you are given any complex matrix of size MR by MT, and these could be any numbers. This matrix, we call it H, and we can decompose always such a matrix into three matrices, U, sigma, and V. Sigma is a diagonal matrix. Okay, so it only has elements on the diagonal. U and V are unitary matrices of the corresponding dimensions. So let's see. H is MR by MT. Then U, which is at the beginning, should be MR by MR. And U is a unitary matrix. So this means that U Hermitian U is U Hermitian is an identity matrix. So you can interpret U as a kind of rotation in a high dimensional space. V, which is on the other side here, right? And you have at the second dimension of H is the number of transmit antennas, so V should be MT by MT. And V also satisfies this requirement. So it's also a unitary matrix, but U is an MR unitary matrix, V is an MT unitary matrix. And then sigma, which is squeezed in between, should be of size MR by MT. It is a diagonal matrix and it has a certain rank, so that means that it has a certain number of non-zero eigenvalues, a certain number of non-zero singular values. And this number is called the rank of the channel. And this rank of the channel should be less than the number of transmit or receive antennas just because of the size of the matrix. So let's say that MR is equal to 2 and MT is equal to 3. That means sigma is a 2 by 3 matrix, right? So it can have a value here and a value here, and then of course the rest will be zeros. But you see that you can only have up to 2 non-zero singular values, right? Just because you only have 2 receive antennas. Similarly, so this is one example. If MR is equal to 3 and MT is equal to 2, right? How sigma then will look like? It's a matrix like this. There's a diagonal where you could have some non-zeros, but on the off diagonal you will have zeros. Okay, so again, your rank can be at most 2, or the number of non-zero singular values can be at most 2. It could be less as well. So it could be that the second element is also 0. Important also in this sigma matrix is that the entries here, okay, so let's say sigma II, they satisfy 2 things. So one is that it is real and greater than 0. And the second thing is that sigma II is greater or equal than sigma I plus 1, I plus 1. So they are the singular values, which are the elements of the sigma matrix, are ordered from large to small. Good, and then we will use this information now to work with our MIMO channel. So I will go through this again because I think it's an important topic. So any complex matrix I can decompose as a product of 3 matrices, U, sigma, and V Hermitian. U and V are unitary matrices of the correct dimensions. Sigma is a diagonal matrix, is the matrix of so-called singular values. These singular values are all real positive numbers, and they are ordered from large to small. The number of non-singular values is called the rank of the matrix, and this rank is always less or equal than the minimum of the number of receive and transmit antennas. Good. And you can read more about this on the Wikipedia page, and there's also, I think, in the matrix cookbook. But now let's accept this as a truth, and now we will use this in our MIMO system. So recall, we have our channel between transmitter and receiver. We have our things we send over the antennas, and then we have the things that we receive on the antenna. So I will maybe draw another block diagram. We have our transmit antennas. No, let me do 2 transmit antennas. We have our receive antennas. Let's say 3 receive antennas. What we send is X1 and X2. We receive Y1, Y2, Y3. And what we will now do is we'll apply some additional processing here and some additional processing here. Okay. The processing that we will do is as follows. At the transmitter, we will pre-multiply what we want to transmit with the matrix V, where this matrix is this exact matrix here. Okay. And then the input to this pre-coding operation, these are our data symbols. So these are our QAM or PSK symbols. We will multiply them with V, and then the result we call X, and that's what we send over our channel. Okay, so we'll have here X tilde 1, X tilde 2. We multiply by V, and whatever is the result, that's what we transmit over the channel. Then we have our channel H between the transmitter and the receiver. We have our observation Y, okay, and again Y is Hx plus N as before. What we do now at the receiver is something called shaping. We apply with U Hermitian. And the output we call Y tilde. So at the receiver we apply U Hermitian, and we have Y tilde 1, Y tilde 2, Y tilde 3. And we will now try to determine what is the relation between this Y tilde and these X tildes. And that's what's written down here. Okay, so Y tilde is U tilde times H times V times X tilde. Y tilde is U Hermitian times H times X times V times X tilde plus noise. And this noise is U Hermitian times the original noise. So let me call this the bar and bar. Now I expand H again. So I know that H is U sigma V Hermitian. I write it in here. And what we see is that U Hermitian U is an identity. V Hermitian V is also an identity. So this means that this is X tilde plus noise. Now this noise here is not enhanced in any way because this is a unitary matrix, and the unitary matrices do not enhance the noise. They keep the noise variance the same. So what we've created is RH parallel channels, right? Because each Y tilde depends, each element here depends on one element here plus noise. The noise statistics are not affected because we multiply with a unitary matrix. Because we've created parallel channels, we can apply this with water filling, so power and rate adaptation, and detection becomes very simple. And I think in the next slide, let's see, we will do an example of this. But before we go to the example in the slides, let me do another example just to reinforce these ideas. Hang on a sec. So let's suppose that you have a MIMO system with a transmit array. So here You have your transmit array. And let's say that the number of transmit antennas is 10. Then you have your receive array. And let's say the number of receive antennas is 20. Okay. Then you have your channel, which is a 20 by 10 matrix. It's a large matrix. Let's now say that we do an SVD on the channel, right? And this gives us our three matrices, U, sigma, and V. U is 20 by 20, V is 10 by 10, and sigma is 20 by 10. And this sigma matrix is a diagonal matrix, so it's a 20 by 10 matrix, so it looks like this. So it can have at most 10 non-singular values. Okay, so these are the singular values, so 10 non-zero singular values. But let's suppose that if we were to plot these non-singular values from 1 to 10, so we plot sigma II, here is I, and let's suppose for the first singular value is large and all the rest is 0. This can happen for some channels. So this for instance happens when your channel is equal to this A alpha A theta A transposed phi. For these geometric line of sight channels or single path channels, you will have such a case. So you can even try this yourself. Good. And now we apply our precoding and combining technique. So we have here V and U. We have then our data symbols, x tilde 1 till x tilde 10. Here we have y tilde 1 till y tilde 20. Okay, and now we know from the math, so let's see that what I'm transmitting is x, which is vx tilde. Then we have the channel, which is h. What the receiver sees is y, which is h times x plus noise. The receiver then does shaping. Shaping is also sometimes known as combining. So it computes a new observation. We call this y tilde, which is u Hermitian times y, which is u Hermitian hx plus u Hermitian n. Okay. And now this noise here, okay, let me call this w, has the following properties: that the covariance matrix, which is the same as, let's see, u Hermitian n and Hermitian u, which is u Hermitian expectation n and Hermitian u, like this, which is n naught. Okay, in this case we actually said the noise variance is 1, but in general n naught. So 1 times u Hermitian u, which is 1. Okay, so the noise after applying u Hermitian is the same as the noise before applying u Hermitian. And then we can plug in what is x. This is u Hermitian h, and we see that x was vx tilde, okay, so vx tilde plus our noise. Now we plug in what is h, so u Hermitian, okay, we plug in h, and h is u sigma v Hermitian v x tilde plus w. I've not been very consistent with my underlines, but okay. So this is h. And now we know that u Hermitian u is an identity matrix, so this is gone. V Hermitian v is also an identity matrix. So what we find is y tilde, okay, I shouldn't use, okay, y tilde is equal to sigma x tilde plus w. Okay, these are all vectors. Good. We recall what sigma looks like, so then we can say y tilde 1 is sigma 1, 1, x tilde 1 plus w tilde 1. Okay, that's the first entry in y. Y tilde 2 is sigma 2, 2, x tilde 2 plus w tilde 2. And so forth up until y tilde 20. Okay, sorry, let's go back up until y tilde 10, which is sigma 10, comma 10, x tilde 10 plus w tilde, y tilde, I don't need to put tildes, w1, w2 plus w10, and then y tilde 11. But now you see there's no sigma 11, 11 because the matrix is not a square matrix, so then I have just noise. 11 y tilde till 20, 20, sorry, till 20 is equal just to noise 20. Good. So now we can draw a number of conclusions. First of all, the observations y11 till y20, they're not needed because they just contain noise, so we don't even need to compute it. And secondly, in our case, in a specific example, only sigma 1, 1 was not 0, right? So actually, this is just noise. W10, this is W2, these were all noise. And this is now sigma 1, 1, x tilde 1 plus W1. Okay, so again, all of these are not really needed, so we cannot transmit anything. And we only have this observation here. So we see, now if we go back to the block diagram on the top here, among all of these transmitted symbols, we actually only transmit one. Okay, so here we don't transmit anything on the symbol on stream 2 to 10. So we transmit zeros, only we transmit on the first entry of this vector. And on the receiver side, actually, all of these outputs we don't need to compute, we just care about the first output. So there are outputs here, but we don't care. So we've now created a SISO channel, right? So this whole system now, from end to end here, has become a single input, single output channel, where y tilde 1 is sigma 1, 1, x tilde 1 plus noise, W1. But in order to create this SISO channel, we use the full channel matrix, and we use V and we use U. So this is not the same as just sending something on the first transmit antenna and receiving on the first receive antenna. We really combine all the information from the whole channel using V and U to create this SISO link. Good, all right, so let's take a break and then come back with an example.